Hello and welcome to another lecture on control. Today's topic is on the AutoRegressive eXogenous model, also known as the ARX model. So after today's lecture, you should be able to explain the need for difference equation and how to convert from g of z, so your discrete time transfer function, into g of z minus 1. And then finally into the AutoRegressive eXogenous model. So we've seen this form before, so the sample data control system. Last few lectures we were looking at discrete time modeling and control of the control algorithm. So if you remember, we discretized from a continuous controller and ended up with a discrete time proportional, integral and derivative controller. And the one area really we haven't looked at, so what further considerations perhaps do we look at, is the continuous system. So far we've looked at modeling it in the continuous domain, and then we've discretized it into getting effectively g of z, so getting us a g of z transfer function. So what we're going to look at this week is looking more at the practical aspects of that g of z, because if you remember from one of the early lectures where we talked about simulation, and simulation being kind of like time, t, 2t, 3t, 4t, like forward time as you can see here, so k, here you can see k and then k plus 1, k plus 2, k plus 3. Okay, in terms of control, that's really not practical. So what we usually use for control is past measured values. So in this case, k being the current sample, k minus 1, the previous sample, k minus 2, previous two samples, with those samples obviously with the interval that determined based on the sample interval. So that moves us on then into kind of the idea of using difference equations, where we effectively have kind of the system output being represented by a linear combination of past inputs and past outputs, which are available because we can effectively store them in practice on the microcontroller. So the form of the difference equation that will lead to is that, as we spoke about, is this AutoRegressive eXogenous model, or the ARX model, and this is what we use for when we get on to linear least squares that we'll talk about a little bit more, but based on kind of known input data and also measured output data, and putting it into this form, so the ARX model, and we can effectively apply least squares and then identify what the parameters are of the system based on known input and output data, known / and measured input and output data. That's something. Watch the next lecture video and you'll see on least squares. So consider the following z form transfer function. So this is what we've seen previously. What the first step we want to do is to convert from g of z, okay, into g of z minus 1. So what we need to do this is effectively divide through by the highest power. So in this case it's z squared. So if we divide through by the highest power, effectively z divided by z squared is going to give us z minus 1. Z divided by z squared is going to give us z minus 1, as I've just said here. There's no z term here, so you're just going to get z minus 2. You're going to get z squared over z squared is going to give you 1, minus 1, and then likewise on the numerator it's going to give you minus 2. So that there is your transfer function subject to g of z minus 1. Now that's the form of it. Next step, what we're going to do is we're going to take out the common factors, so z minus 1, so this term here in the numerator. If we move that outside, put brackets, so put a 1 here, z minus 1 multiplied by z minus 1 will give us z minus 2, so that's all correct. Where in this case, z minus 1 denotes a delay of 1 sample. So it's always possible to factorise out z minus 1 there. And also an important property to know is that, in terms of when your continuous time system, so if you were to convert this back to the continuous time, so to get g of s, you would have no delays. However, when you move on to the discrete domain, note that there's always a delay of at least 1 sample when dealing with a discrete time system. i.e. it's effectively a delay, a system delay before the input, denoted UK, has an effect on the output, denoted YK, where k denotes the discrete time. So just beware the input's applied, and there's always at least a delay of 1 sample before you see the output. So we now express the discrete input-output system as follows. So here, this is what we've just captured. What I'm going to do is effectively cross-multiply by this. So effectively the denominator here. So you can see that's effectively going to multiply by y of k. Hence you end up with that. And then u of k, so if I multiply from across by u of k, obviously u of k there and there are going to cancel, and it's just going to be that there multiplied by u of k, which is given here. Then if I expand out, so y of k, obviously just multiply, so y of k, it's going to be y of k multiplied by that term there, so you can see, and then y of k multiply that, you can see there. And then likewise here, so z minus 1 multiplied by 1 is going to give you that there, and then z minus 1 0.5 minus 1, so it's going to give you minus 2, so it's going to give you that. And then just remember, okay, I said just remember then you've also got this u of k because it's outside the brackets, the u of k and u of k here. So if we make use of the backward time shift property, so remember we had z minus 1, when that's, in that case, is acting on y of k, it's identical to y of k minus 1. So if you're looking at this, effectively just replace the term when you see kind of this term here, for example, just replace that with y of k minus 1. As you can see, I have done down here. And when you get it kind of when it's minus 2, the only thing that changes really is this in value here. Okay, and likewise here, so it's minus 1, but the only thing is obviously u because it's the input, and then z minus 2. Again, that's just going to change, that becomes that. Rearranging, because what we want to do is we want to make y of k the subject, so you can see y of k is equal to, you'll see y of k is equal to, because what I've done is I've just kind of moved that over to the other side, so plus that, and then you can see then, so that becomes a plus here. Move that over to the side, so plus that, take away that, and then you see that's obviously plus, now that's negative, and obviously these are as they were before. And this form is known as the AutoRegressive eXogenous model, or the ARX model. So this form here. So in terms of the transfer function, so that's the transfer function we were working with. The notation we normally use is to denote the numerator, we use b, so bz of minus 1, and the denominator a of z minus 1. Here you'll see that z of minus 1 outside there. But that's normally the notation, so b and a, so b over a. So in general, the polynomials are given by this. So if we're looking at a, effectively the a terms here, so this here, because it's second order, you can see in this case that there is a2, here a1, and here a0. And then if we then look at the numerator, you can see we've got terms that correspond well, effectively to that. So you can see here, this is b0 and this is b1. So remember an, so where orders of the respective polynomials, so an and nb, an is going to always, well, it's going to be greater or equal to nb. And the leading coefficients, it's worth noting this, that a0 in this case will always be equal to 1, and b0 here will never or won't be equal to 0. So if we're talking about if we're looking now back at the ARX model, where it's given by this form, so a1, a2, b0, and b1. So you can now see the relationship between, well, if we go back previous one, you'll see that in this case here, this is a1, a2, B0, so it's 1, and then B1. So to estimate these coefficients, A1, A2, B0, and B1, we use this past measured outputs and known inputs within a kind of a least squares, linear least squares algorithm, as we'll go on to in the next lecture, and we can effectively estimate what these coefficients are. So I've got here a couple of exercises for you to have a go at. So I want you to convert the following Z-form transfer function into the AutoRegressive eXogenous model. So this transfer function, so it's similar to what we had previously, and then exercise 2 again is similar but with a slightly different form of the transfer function. So in summary, I've introduced you to the practical form of g of z, so i.e. g of z minus 1, where we effectively look at past measured outputs and also past known inputs. And I've also introduced you to the autoregressive eXogenous ARX model that we'll use for least squares, linear least squares in the next lecture. So hopefully by now, you after you've done kind of the exercise, you're able to explain the need for a difference equation to convert from g of z to g of z minus 1 and then into the ARX model. And I think it'll become more obvious when we move on to looking at least squares why this ARX model is important and why g of z minus 1 is also very important. So if you have any questions, please feel free to contact me. Thank you.